Okay, before we start with the lecture, there's just a few things we need to go through. Okay, firstly, in the last lecture, I told all of you to go through the Learn page and then go through the modules, rules, and procedures form. Yes, so if you follow the link here, just click on the link there. You'll get to this page with all the rules for the module. So this is specifically for the maths, but you'll have a similar thing for the other modules. Right, just lectures, missing assessments, cheating, clashes, right, just things like that. Please read through that, fill in your details, and there's just a little agree button at the bottom here. Please make sure you do that before the first quiz that we have next week, Tuesday. If you do not fill in this form and click the agree button, your marks will be withheld. Okay, which means after the first week, your class mark is 0 until you fill in this form and click agree. Okay, so far, very few of you have filled it in. I got everything here. Here's the MATH160, 15 out of roughly 100 of you. Okay, so these 15, they will be getting their marks next week. The rest will not be getting their marks next week until this is filled in. Okay, is everyone clear on that? Yeah, please make sure you do that as soon as possible. Okay. And then next, your group assignments. So if you go down here to the tutorial group assignments, you'll see the list over here with everyone and their group that they're in. Okay, sorry. Let's go here. Okay, so you go down. So after this weekly tutorial work, you'll see tutorial group assignments and then the list here. Okay, you go to the list here, it will have all of your student numbers. You just find where you are, and it will have your group next to it. Okay, so each of these groups, so A, B, C, D, E, F, whatever group you're in, you will have an assigned tutor. So you go to that tutor for help, and once you're done with the tutorial work for that hour, you then go to that tutor and they will check you off the class list. Okay, so you can't go to any tutor. So if you're in group A, you go to tutor A, he has the list for that group. You go to someone else, they don't have the list, you're not going to be checked off for that. Okay, so just to give you an idea of what these assignments are going to look like. Of course, you can use your books, you can talk to your friends, you can do whatever, as long as you get them done. So they'll look something like this. Yeah. I had it somewhere here. Okay, I'll post one online you can have a look at. Very simple assignments. So you have the full hour to do it. You probably won't need that time, but it'll just be based on whatever we covered the previous week. So this week is on set theory. So you have the hour to finish that assignment. You show your tutor, they'll check you off the list. And then we have the quiz. Okay. So the quiz, I can show you, it will be something like this. Okay, just roughly MCQ kind of stuff. So you'll have 10 questions on set theory, something like that. And then 2 written questions, something like this. Okay, so this will be the written part. You will then need exam pad or something with you. You write this on paper and then you submit that at the end. This MCQ part over here, this will be done online. Okay, so MCQ stuff done online. Then you'll see the written parts, something like this. That will be done on paper and then you submit that. Okay, and then that will give you your 2 marks for the week. Everyone clear on that? Yeah. This is the only thing for marks each week. The tutorial assignment is just to check if you have any weak areas before you write the quiz, right? So if you can finish the assignment and the tutor says, no, you're good, then you have no problem writing the test. If the tutor says, no, you're missing something over here, you can quickly read up on that and then you write the quiz. Okay. So there's no, surprise, oh, this is coming in the quiz. You know ahead of time what that's going to be. Okay, everyone clear on that? Okay, let's start off with the lecture. So today and tomorrow, we're going to go through set theory and logical proofs. So last time, some of you did mention you did some proof techniques, so that will help you a little bit. But we'll start right from the beginning so no one's left out. Now, at university level, we work quite quickly. So every week will be roughly a chapter, chapter and a half. So as I go through the lecture, right, we will build up the pace as we go through. If at any point you're lost, you put your hand up or you call out, you say, "Sir, I'm confused. Please do that a little bit again," and then I'll do that. If you sit in silence and you fall behind, no one is going to be waiting for you, right? We have a class of 100. If you sit right in the back and you have a question but you don't ask, guess what? 99 of the other students, they're working ahead. Okay. And as soon as you fall behind 1 week, the next week you fall behind even more, and so on. When it comes to the test, you're completely lost and you're all anxious, and then you come see me in my office. You say, "Sir, please help me," and now you're 3 weeks behind in work. Okay. So please, from the very beginning, make sure you keep up with the work. If you are falling behind during the lecture, let me know. I can help you out. Otherwise, you're on your own. No one else can help you at that point. We clear? Yeah. If you're shy, sit next to someone that isn't shy and tell them to ask the question. Yeah. Yeah. You shy. Okay. You shy, you ask the guy next to you. He can ask the question, but make sure your question gets asked. Okay. Everyone clear on that? Okay. Let's get started. So we're going to start off with set theory and then move on to logical proofs. We're not going to do very strict set theory. That does exist. That's for the scientists on Westville. We're going to do a very rough definition of set theory and do it more by example than strict definition. Okay, so a very rough definition to start us. Stamp pen. Oh, there we go. Okay, so this is a very rough definition, so just keep this in the back of your mind as we go through this. So a set is a collection of objects. Okay, very rough definition, but you should be familiar with this from high school. Okay, so these objects are called the elements of the set. Okay, so a set is some collection. Within that collection, we call those things the elements. So given an object X, so now I'm not saying what X is, it's an object. Later on, X could be a number, it could be a function, it could be a function of functions. For now, we just call it object. Later on, when we look at a specific context, then we'll give that a specific name. But for now, it's just object. So given an object X, it can either be in the set, and if it is in the set, we write X. We use the Greek letter epsilon. It looks like that. And then the set S. So, for example, we can call it S. So a little bit of notation. Usually when we refer to the elements, we use lowercase. And if we're referring to sets, we use uppercase. That's the convention we'll be using. If you decide to swap that in a test, I'm going to be a bit confused. Maybe I'll see what you're talking about, but rather stick to this. Okay, so elements of a set, lowercase, the set itself, uppercase. All right, it's not strict, but it's preferred to do it this way. So here we read this whole symbol all together. We read it as X. is an element, right? Because if it's in the set, we call it an element of S. Okay, so it is either in the set or not in the set. Has to be one of those two. Okay, and if it is not in the set, we use the following symbol, X, again, that epsilon symbol, S, but we put a line through it. So when you put a line through something, it means not whatever that is. So you might be familiar with 1 equals 2. That's wrong. 1 is not equal to 2. You put a line through it, right? 1 is not equal. Okay. So whatever symbol you have, if you put the line through it, it means not whatever that means. Okay. So here we read this as X is not an element of S. Okay. So that's how we read that symbol. Now, if it is not an element of S, it's an element of another set, which we call the complement of S. So we can view that as a picture. So let's say we have some larger space. We'll see what this means later on. If we have our set S here, you can either be in the set, so you're within that shaded part there, or you are not in the set, which means you're in the complement. We call that S with a bar on the top. There's some other notations. So S complements. So that's how we write it. It was either S bar, S prime, or S with a little c. Okay, so we'll use these different notations. You're free to use whichever one you want, right? S bar, S prime, S with the little c at the top. You're free to use that. Make sure you know all three because you don't know what's coming up in the test. So if I use S prime in the test, you need to know that that means complement. Everyone okay so far? No one lost yet. Okay. We can explicitly write out the elements of a set using the bracket notation. Okay, so let's say we have a set S. It has some elements in it. I want to tell you what those elements are. We can use the following notation for that. So let's say we have the set S. We use a curly bracket or brace, and we can write out the elements. So let's say we have 1, 2, 3, 4, 5, and then we have the closing bracket or closing brace. So here we have a set S, and those are its elements. Okay. Or we can have another set, let's say U, again, open brace or open bracket, let's say apple, orange, pear, close brace. Okay, so these are two different sets. They have these elements. In the first set, it has the elements 1, 2, 3, 4, 5. In the second set, it has the elements apple, orange, pear. Remember at the beginning, I said a set contains objects, right? It doesn't matter what those things are. In the first case, it contains numbers. Those are the objects. In the second case, it contains fruits. Those are the objects, right? So in general, we say object. If you want to get specific, you need to write out the set to show what it is. Okay. The number of elements in a set is called the cardinality. Okay, so that's the definition for this word. Sure, you've heard it before, but we have the cardinality of the set is the number of elements, and it's given by the following notation. So we'll do the example for these two. So the first one, S. we use our absolute value symbol, the vertical lines. So S like this. This means the number of elements in that set. So here S has 1, 2, 3, 4, 5 elements. So the cardinality of S is 5. Okay, in the second case, we have 1, 2, 3 elements. So the cardinality of U is 3. Okay. A set may have infinitely many elements. So we say it has infinite cardinality. We're not going to be looking at that too much. Okay, so for these simple examples, they will all have finite cardinality, so you can actually count them or calculate them in some way. So infinite sets, for the set theory part, we're not going to be looking at that. If a set has no elements, so it has cardinality 0, then we call it the empty set. Right, quite an obvious name, set with nothing in it, empty set. Okay. And it has the notation circle with a line through it, so Greek letter phi, if you know your Greek. So that's the symbol there. Or we can write it as open brace, but the set contains nothing, so we're not going to have anything in the set, and then closing brace. Okay, those are the notations we're going to be using for the empty set. Okay, and again, open, close, there's nothing inside, so again, it has no elements. Okay, and we can write that explicitly as the cardinality of the empty set is 0. Okay, and it is the only set to have 0 things because the empty set is unique. There's only one set that has nothing in it. Okay, any questions so far? Okay, if you think this is boring, just wait 2 minutes and then it won't be boring anymore. Okay, right, we have to start somewhere, so we start from the beginning. You'll see it ramps up quite quickly from here. Yes. Sorry? No, I can't hear you. You have to shout. Oh, the symbol. Yeah, so this is the symbol for the empty set. You can Google, it's the Greek letter phi. So it's a circle, which is with a line through it. Okay, it's just the name that we give to that set. Yeah, it's a Greek letter, so you can just look that up. Yeah, so this is just a name. Right, we could have called it E for empty set, but, someone chose that. Okay, any other questions? All good. Okay, so I'm taking it as we're all on the same page now with the basic set theory. Okay, so from now on, you may have not covered this in high school, so we're going into the university stuff. Okay, so we can also define a set implicitly. Implicitly. By a rule function that determines if a given object is an element of the set or not an element of the set. Right, I call it object here because we don't know if it's in the set. If it's in the set, it's an element. If it's not in the set, it's not an element of the set, but it is an element of the complement. So again, we just call it object. Later on, we'll give it a specific name like number or function or whatever. Okay, defines if an object is in the set or not in the set. Right, it can only be one of those two, like we had at the beginning. Okay, and we write the following notation. This is called set builder notation, also known as restricted comprehension. So we're going to call it set builder notation. If you're doing pure maths on Westville, they would call it restricted comprehension. You still need to know what it means though. So very similar to what we had before with those sets. So we have a set S is equal to, and we still use that brace notation or the bracket notation, but we write X as in the object X that we're deciding, is it in the set or is it not in the set? Then we have a vertical line, which we read as such that. I'll put it all together at the end. So X is an element of the set such that, and then we have the rule. That will be R of X. Okay. So what is this R of X? This is some rule. Okay, that tells us if the object X is in the set or not in the set. Yeah, and it does that by answering a question. It's just a yes or no question. So R of X, if you put some X, R of X is either yes, it is in the set, or no, it is not in the set. Another way of saying it is true or false, right? You all know the binary true or false. So it's either yes, it is in the set, or no, it is not in the set. Or another way of phrasing it, it's either true, so it evaluates to true, as in yes, it is in the set, that's true, or it evaluates to false, as in it is not in the set. It's binary, it's one or the other. Okay, yes, no, true, false. In the set, not in the set. Okay, so R of X can take two values, true or false, like we said. So we write it explicitly as R of X true. If it does evaluate to true, this implies, so this means that, so if that left-hand side is true, then we have the following. X is an element of the set, and we know what that means from before. And the only other thing it can be is not in the set. So if R of X evaluates to false, then this implies or means that X is not in the set. Again, binary. It's always one of the other. Okay, is everyone okay with that? Okay, so we've got some rule, whatever it might be. It can either be true. Yeah. Which part? The rule. Okay, so maybe we can look at some examples as well later, but this rule is just some rule that you come up with. Yeah, if I give you an object X, if the rule returns true, then that object X is in the set. If the rule returns false, then it is not in the set. Okay, for example, let's say all of you go outside the class, and I say the rule for being in the class is you're male. So all of you outside, and we go one by one. You come to me and I'll say male, female, yes, no, true, false. If it's true, you come in the class. If it's false, you're out of the class. After we go through every single element, who's in the class? Exactly, because it's all the elements or the objects that satisfy that rule. That rule is whatever you want it to be. So we'll see some examples, but it's always the case that you take your object X, you look at the rule, and you ask yes or no. If you say yes, then it is in the set. If you say no, it is not in the set. Okay, it's very abstract for now, but when we look at the examples, you'll see it's quite easy. Okay, so let's have a look at some examples. So example number 1, we have the set S. And we're going to use this new set builder notation or restricted comprehension. So we have all the objects X. Okay, that's everything that we're looking at. And the rule is the following. X is an integer. Now, can you answer yes or no to this question? If I give you an X, can you answer yes or no whether it's an integer or not? Yeah, so it's a rule. So I give you an X, let's say car. Is a car an integer? No. What happens if X is 2? Is 2 an integer? Yes. So in the first case, you answered no, not in the set. Second case, you answered yes, it is in the set. That's all you're doing. Now I'm going to make it a little bit more complicated, and I'm going to say and 0 is less than X less than 7. Let's look at that second part. If I give you an X, okay, let's say it's an integer from the first part, can you answer yes or no as to whether it's between 0 and 7? Yes. Let's say minus 1. What's the answer? Yes or no? No. If I give you 3, yes or no? Exactly. So you can answer yes or no for any X. The ones you answer yes to, those are in the set. The ones you answer no to, those are not in the set. And we've got an and between them. So it must be the first one and the second one. Both must be true. Right? Everyone understand that bit? Okay. Well, so let's try to write this out. We know what the rule is. Let's go through every single X and check, does it satisfy the rule or not? Now, obviously, we don't need to go through every single integer, but you get the idea. So let's look at that second part. Okay, so we look at the first one. We know it's an integer. Let's look at the second part. The X that answers yes will be the ones between 0 and 7. So we just check. 0, does that satisfy that rule? No, it doesn't, right? Because it's less than. What about 1? So we can put a 1. You guys say yes, we put a 1. 2, we put a 2. 3, can put a 3. 4, yep. 5, 6, 7, no. Anything after 7? No, so we stop there. That's it. Okay, so here, instead of writing that set 1 to 6, we wrote it using that rule. But these are equal. You can either write out the elements like we did at the bottom, or you can specify the rule. Sometimes it's easier to specify the rule. Sometimes it's easier to write them out. That just depends on the problem. Okay, and you should be able to go between the two. So if I give you that bottom one, you should be able to write it as a rule. If I give you the rule, you should be able to write the bottom one. Okay, you should be able to go between the two. Okay, number 2, S is equal to all the X. We don't know what those are, and we have a rule to go with it. X is an integer, and X is odd. Okay, so from the first part of the rule, we know it must be an integer, so we know what we're working with. The second part, X is odd. So let's go through them. Okay, let's start from 0. 0, is that odd? No, 0 is even, so that's not there. What about 1? Okay, so we put a 1. 2? No, so we don't write it. 3? Yep, so we write it. 4? No, we don't write it. 5? Yep. And you get the idea. We can put ... because this is an infinite set. So you'll spend your whole life writing it out, so we don't do that. We just put a few elements and then ... We know what the pattern is. The pattern is just whatever rule we had there. Okay, so this is an example of an infinite set. Okay, any questions so far? Yep.
How many rows should we write down until you can say it's infinite?
Just a few. Yeah, we're not in baby school. You know, if I know it, you know it, we all know it, that's fine. You write 1, 3, 5, we all know it means the odd numbers. If you just write 1 ... you know, that's a bit of confusion. Yep.
Empty set.
Empty set is defined to have no elements. Yeah, so empty set will have nothing in it. Okay, always. So here, if we go back to the definition, here, it's defined to be this. So you pick any X, it is definitely not in that set. So you can write it out if you want. So any X is not an element of the empty set. You can define it like that as well. Okay. So you can define it this first way, or you can define it the second way. It's the equivalent. Okay. Any other questions? Yeah, I think you get the idea. Let's do one more example. Number 3. So we have S is equal to the set with X. Again, we don't know what X is. We need to check. X is even. Or X is prime. Okay. Now it's no longer and, it's or. So it means one of these must be true. So for and, it's this and that. So both must be true. In this case, it's or. So it's the first one or it's the second one. Okay, so let's have a look. Okay, so let's start off with 0. Is 0 even or is it prime? Yes. All right, it's even, so that's all we need. Okay, it's only one of them that needs to have the yes. So yeah, that's fine. 1. Is 1 even? No. Is 1 prime? No, it's not. Prime start from 2. Okay, so 1 is not even. It's not prime. It's neither of them. It's not in the set. So 1 we leave out. What about 2? Is 2 even? Yep, that's fine. We don't even need to check the second one as long as one of them is true. So we can put a 2. 3, is 3 even? Okay, that's fine. We can still check the next one. Is 3 prime? Yeah, so one of them is true, so we can write it down. Let's do one more. 4, is it even? We don't even need to check the next one. It's even, we can write it down. And, oops, sorry, dot, dot, dots, this continues forever. Okay, so we have another infinite set. So you can either write all of the elements out, which is impossible. So instead of that, we provide the rule there. Okay, is everyone okay with this set builder notation? Okay, this we're going to be using a lot throughout this year and next year. Okay, whenever we want to have a set of something and we want to know exactly what's in it, we have to define it like this, right? Because some of these sets we can't even write out. The only way to write it out is with that rule. Okay, sometimes these rules get very complicated, but we'll get through it. Okay, so we're all clear on what a set is. Next is subsets of a set. Okay, so let B be a set. And now when I say set, you know what that means, right? It's either a collection of objects where I write out everything explicitly, or it's a collection of objects given by the rule. It's one of those two. Okay, so when I say set, you know what I mean. So let B be a set. A is a subset, okay, of B. And we write this notation, A subset B. It's almost like less than or equal to, but it's a bit more curvy. Okay, so A is a subset of B if all the elements of A are contained in B. Okay, so A is a set just by itself. We know what that means. But in this case, we write it relative to B as A is a subset of B. Okay, in other words, B contains A. It's a smaller set. Okay, so we can write it as a picture, or we can write it algebraically. We'll see. So let's say we have this big space we call B, set of something. A will be a set within this larger set. Something like that. Okay, very obvious kind of picture. Okay, otherwise we can write it as x elements of A. So if x is an element of A, then x is an element of B. In other words, with that first part, if we already know it's an element of A, so that's given, we automatically conclude that x is an element of B. We get that part for free. If we know it's in A, it's automatically in B. Okay. First homework for the year. Prove the following. If A is a subset of B and B is a subset of A, then the sets are equal. Okay, so think about that. You can prove it however you want. As long as it's mathematically right, then it's fine. So think about how you're going to do that, and we'll check that tomorrow. Okay, so we know A is a subset of B, B is a subset of A, show that they must be in fact equal. Okay, quick example. I'm sure you all understand the concept. Let's say we have B is the set 1, 2, 3, and A is the set 1, 2. Here we can see that A is a subset of B. We can check this for each element. So 1 is an element of A. Is 1 also an element of B? Yeah, so that's fine. So we check the statement here. 1 was an element of A. 1 was an element of B. So check. That's fine. Let's check the next one. 2. 2 is an element of A. Is 2 an element of B? Yep, both of them checked. So it is a subset. Now, if it looks like this, just very simple sets, it's easy to check, right? We just go through each element and we can see. What happens if A is defined by a rule? So it's using set builder notation, and B is also defined by another rule. Now it's a bit more difficult to check. Okay, so for these examples, it's easy. We have 1, check, 2, check, that's fine. For more complicated examples, you need to check the rules. And we do that using the statement here. So you check the rule for being in A, right? X elements of A. If that rule is satisfied by X, then the rule for B is automatically satisfied as well. Yeah, does that make sense? So if you satisfy the rule for A, you're in A, X elements of A, then you must also satisfy the rule for B, X elements of B. You just check that the rules match up like that. Okay, so this is example 1. Example 2. Let's say that set B is the natural numbers. We know what that means. Just to avoid any confusion, when we say natural numbers, we start from 1, always. This year, next year, that's the convention we use. Okay, so in some places, you'll see natural numbers starting from 0. We don't do that. It just causes problems. We start from 1. So if you need to make a note in your book, just do that now. Okay, so B is that. And A, we're going to use some set builder notation, X, such that X is even. Now here, we can't just go element by element and check. We have a rule. Okay, so the rule for A is X is even. The rule for B is it must be a natural number. Now we check the condition. If X is even, is it also a natural number? Yes or no? Yes. So if I give you an even number, you look at it, it's also a natural number. So the even numbers are a subset of the natural numbers. Does that make sense? Because if you're even, you are also a natural number. So if you are in the set A, you are also in the set B. That is the definition for subset. Okay, number 3. B, so we just have the set B. and we have itself. So we have two sets, B and a copy of B. And the question is B a subset of B? Well, we just check the conditions. So we take an element from B. Is it in B? If I take something from B, is it in B? Yeah, obviously. So B is a subset of B. It satisfies the rule. So any element of the set is also in the set. So B is a subset of B. Okay, and number 4. Let's take the empty set and some set B. This one's a little bit tricky, but we just need to think about it logically. What is the condition? Every element in the first set must be in the second set. That's the condition we need to check. We need to be a bit careful about this. Okay. We need to check every element in the first one and check, is it contained in the second one? What are the elements of the empty set? Nothing. So there's nothing to check. So what does that mean? It is a subset. If there's nothing to check, then there's nothing to make it false. So the default is true. Okay, you need to think about that for a bit. Okay, go back to the definition. So we look back here. If all the elements of A are contained in B. Now you can't think naively about this. You must be very logical. All of the elements of A are contained in B. The empty set has no elements. So the statement is true. Okay, you have to wrap your head around. I can't explain more than that, right? So all of the elements. How many elements are there to check? None. There's no elements to check. So can that statement ever be false? Are there any elements to make it false? No. If there's no elements to make it false, it must be true. Make sense? Okay, that's how you need to be thinking with maths. Okay. Remember, it's either true or false. There's nothing in between. If there's nothing to make it false, what is the only other option? True. There you go. Okay. So you need to start thinking more mathematically than just thinking about the definition just as is. Okay, everyone okay with that? Okay, think about it for a bit. Maybe tomorrow morning when you're having breakfast, think about it again. It should click. Okay, next, a proper subset. Okay, so this is just a general subset. Now we're looking at specifically a proper subset. So the word proper in front of it, it adds an extra condition. So A is a proper subset of B, proper subset, if, and now there's two conditions. Number 1, it must be a subset from the name. So number 1, A is a subset of B. And we know how to check that condition. Right, just go up a bit. We know how to check that. Number 2, A is not equal to B. So condition number 1 means it is a subset, the second word. Condition number 2 is what makes it a proper subset. Okay, these are two different things. So you may have a subset, but it may not be a proper subset. There's an extra condition attached. Okay, and the notation is a proper subset of B. Notice that little line underneath is missing. So the way to think about it is, for example, 1 is less than or equal to 1. It's less than or equal to. Can be equal, right? But 1 is strictly less than 2. We don't put that little equal sign bit. Okay, so 1 less than or equal to 1, that makes sense because it can be equal, but strictly less than, it can never be equal. So you cannot write 1 is less than 1. Right? That's rubbish. 1 less than 1 is nonsense. Okay, so we write the same sort of thing here. We don't put that little line underneath. So in case you missed that, from here, right, there's that little line underneath. So this is like subset or equal to, like less than or equal to. But for proper subset, we don't put that little line. Okay, please make sure you know the difference between those two. Okay, everyone okay so far? Besides the heat, you're all good. Okay, next, number sets. So these will be the first major sets that we're going to look at. So we're not interested in the sets of cars or anything like that, or sets of fruits. That's all gone now. We're going to be looking at number sets, specifically the sets of real numbers, so that eventually we can work towards calculus. Okay, but before we get to that, just quick revision on the number sets. So the natural numbers, we know what those are. That's 1, 2, 3, and so on. Again, put the little notes. We do not start from 0. Then we have the integers. So Z with that little double line there. This is going to be, well, it's doubly infinite from both sides. So we have all the negative integers. Let's say minus 1, 0, 1, 2, and all the positive integers. Okay. So if it's like this doubly infinite, we put dot, dot, dot in the front because it goes all the way to negative infinity, dot, dot, dot at the end because it goes all the way to positive infinity. Next is the rationals. Q with the little line. We know what these are. These are the sets of all fractions. So we have P over Q, the line such that, remember I mentioned it earlier. So it's all the numbers P over Q such that, and we have a condition. It can't be all the numbers P over Q. Why? There's one important rule that we need to consider. You can't take any P over Q. What can P be for the top? Can it be anything? Sorry? What's that? Yep, that's one thing. We need to be very technical with this. Can the top be pi? Is pi a rational number? No, so we need to remove it. Remember, we're doing this from scratch. You can't make any assumptions. So P and Q firstly must be integers. Yeah, you can't have anything at the top. Remember, these P and Q for the sets are objects. P could be car, could be whatever. We need to say exactly and precisely what P and Q are. So P and Q must be integers. Yeah, you can't make any assumptions. You have to say exactly what you mean. And you said it, Q can't be 0. Okay, you must be very careful when you write things out. If you just write P over Q in the test, I don't know what P is. Where do you get P from? Right? P must be an integer. Q must be an integer. Okay, now I know what you were talking about. Can we divide by 0? No. So you need to write Q cannot be 0. Yeah, again, please be very precise when you're writing things out. Okay. Then we have the irrationals. We just write that Q prime. Okay. It is the complement. You are either rational or you are irrational. One of the two. So we put the little prime, or you put the bar at the top, or the little C, just to show that it's the complement. So those are the irrationals. And if you put the two together, then we get the whole real line. This is the set of all X. Again, X can be anything. 1, 2, 3, car, blue, apple, pear. X can be anything. But we don't want it to be anything. It must either be a rational number. What's the other possibility? You are either rational or you are irrational. And that takes care of everything. That's the whole real number line. So it's either all of the rationals together with all of the irrationals. We call that the real number line. So that was just a very quick way of starting with natural numbers and building all the way up to real numbers. You see how we did that? You start with the natural numbers, you include the positives and the negative versions, you get the integers. You take fractions of integers, you get the rationals. The rationals don't cover everything, so we include the irrationals. If you combine those, you get the reals. And that's everything there. And this is what we need for calculus. Okay. So we're going to be working over the real number line. I'm sure everyone's familiar with the real number line, hopefully. Okay. No hands, so I'll take that as a yes. Okay, now that we know what a set is, we know what a subset is, we have some examples of useful sets. What can we do with these sets? So sets operations. Okay, so given a set or sometimes two sets, what can we do with them? Okay, we're going to look at combining them in certain ways, taking their difference, taking their power sets, and so on. There's a number of things we can do with these sets. So number one, I'm sure you're all familiar with this, the union. Anyone not familiar with the union? You're not familiar. Anyone else? Okay. Okay, a few. Okay, so we have the union. So we write A with a U, but no tail with the U. So it's just like that cup sort of shape. So A union B. This is a new set formed from A and B, and we write it using a rule. So it's all the elements X, again, such that, and we have a rule. If the rule evaluates to yes, then that is in the union. If the rule evaluates to no, then it is not in the union. So what is the rule? The rule is that this X must be an element of A, or X must be an element of B. That's the rule. It must be in one of them. So if you think about it, if it's in one or it's in the other, then it's in the combination of the two. So we can see that in a nice little picture. So we have set A, set B, whatever they might be. So what are all the elements that are in A? That's the first part. So we can shade everything in A. So this first part of the rule, X elements of A, that gives us all of this. Right? Okay, we look at everything. Is it in A? We shade it in. So that's everything in A. What about the second part? X elements of B. That is going to be everything in B. So we shade all of B. And after all of that, we have then shaded the union. Okay, so the total shaded part, we call that the union. Yeah, make sense? Good. Other one, make sense? Perfect. Number two, we have the intersection. Okay, it looks very similar to the union, but please notice the differences. So intersection is A, and then we draw that the other way now. So union is like a U, intersection is the other way around. Again, this is a new set. It is formed from A and B using a rule. Here's the rule. So X is an element of A, and X is an element of B. Okay, again, looks very similar between the two, but please notice the distinction. In the first one, it's X elements of A or X elements of B. In the second case, it's X elements of A and X elements of B. That distinction makes all the difference between the two definitions. So let's have a look at a picture. So you've seen the pictures before, but this specification with or and, that's what I'm trying to get across. Okay, so we've got A, we've got B, and now we need to look at the two things together. It must be in A, and it must be in B. Both of them must be true. So in this diagram, where are both conditions true at the same time? In the middle. Because in that middle part, it's connected to A, so it's in A. And it's connected to B, so it's in B. Both at the same time, so we call that the intersection. Okay. Is that all right? And you can see the difference, right? We put an or in between, we get this picture. We put an and in between, we get a very different picture. So very slight change in the wording we use, we get two completely different pictures. Okay, number 3, the set difference. So we write this as A minus B. Okay. Sometimes you'll see this as A backslash B. It means the same thing, just different notations. This is equal to, again, it looks very similar to the other ones, but please take notes of the differences. So this is X elements of A and X is not an element of B. So again, please take notes of the differences. So for intersection, it was X elements of A and X elements of B. This is X elements of A and X not elements of B. Okay, very, very slight difference. But please take notes of those differences. Okay, if you're just looking very quickly, you might think, oh, it's the same thing. Okay, but you need to be very careful. Okay, number 4, the power set. Okay, so given a set B, the power set is defined as P of B. And this is the set of all A. Okay. Now remember back when I used X and I said X was an object. X could be something. Here, this is a set of A. A is again a set. It is a set of sets. So in this case, the objects in the set are more sets. And the condition to be in the set is that A is a subset of B. Okay. So it is a set of sets. Yep. Sure. Yeah. So we have the set P of B, which we call the power set. It contains all of the sets A. So it's a set of sets now. The condition to be in this power set is that A must be a subset of B. Okay. In other words, it's the set of all subsets. Okay. Yeah, I told you it gets complicated quickly. Okay. So the way to think about this, it is the set of all subsets of B. Now for small sets, we're going to do the calculations to see what this is going to be. For much larger sets, I'm not going to test you on that. You'll be there all day trying to figure it out. Yep. Yeah, so P, that is like the operator. So, like f of x. So it's a function of a set. Okay. So P is the operator of B. A is the subset of B. Okay. So it acts on B and it gives you all of the A's. Okay. Let's have a look at an example. So let's say the set B is equal to 1, 2, 3. Anything more than this, we're going to be here all day. Okay, and we'll see why. So now we need to look at all of the subsets. And we're going to do it systematically. So it is a set. And now we need to consider all of the possible subsets of the set. Now to do that, we need to know the definition of subset. What is a subset? It's a set whose elements are in the larger set. Okay, so firstly, we need to include the empty set. Why? Empty set is always a subset. So we need to include that. Next, so that is the 0 element sets. Next, we're going to consider all of the 1 element sets. So we go through everything and we see which of the 1 element sets are contained. So the set containing just 1. I'm going to write it down and then we'll check. Is the set containing 1 a subset of B? Yes. Because let's look at that set. What are the elements of the set? 1. Is 1 contained in B? Yes. So that is a subset. So again, you need to be very careful with this. Next, the set containing just 2. Now we look at that. Is 2 contained in B? Yeah, that's fine. Next will be the set containing 3. Yeah, so. Okay, 3 is contained in the set. So the set containing 3 is in the power set. Okay. What about the 2 element subsets? So we're going to just go through the list. So what about the set 1, 2? That's a subset. Why? Let's go through the elements. Is 1 contained in the set? Is 2 contained in the set? So we're good. Okay, now that's enough of me. You're going to pick some. We need another 2 element subset. 1, 3. Yep. There's one more. 2 and 3. Any others? No, that's it. Okay. That's all of the 2 element sets. What about the 3 element sets? Yeah, the entire set. The entire set is a subset. So we include that. Yes. Order does not matter. So for sets, remember the definition. A set is a collection of objects. We said nothing about ordering. So you can put it in whatever order you like. It is the same set. Okay. Are you counting them? Are we getting to that now? It's not factorial. No. Okay, so the cardinality of the power set. So this is how you can check that you have all of the elements. Okay, so the cardinality of the power set is equal to 2 to the power of the cardinality of the set B. Yeah. So in this case, how many elements do we have there? In the top there? 3. So the cardinality of B is 3. So how many should we expect for the power set? 2 to the 3? 2 times 2 times 2? 8, yeah. Let's check. So quick count. Do we have 8? Yeah, I'll count them out. Yeah, we got 8. Yeah. So that's how we know if we have all of the elements. Please put a big box around this. This is going to be your tool to check that you have everything. So when answering these questions, if you have less than that amount, you still need to add a few more. If you've got more than this amount, you've done something wrong along the way. Yeah. So the cardinality of the power set is always 2 to the power of however many elements are in that original set. So for homework, let's say we have the set B, and it has the elements A, B, C, D. So we have 4 elements in the set. So how many total subsets should we have? So there's 4 elements. It will be 2 to the 4, which is 16, right? So for homework, write out all 16 subsets. I'll give you 2 for free, empty set and B. Okay. So the rest, that's for homework. Okay, so write it out, see if you can find all of them. So I've given you the 0 element set and the 4 element set. There's going to be 4 1 element sets, A, B, C, D. Then you need to find all of the pairs and all the ones with 3. Okay, so that's for home. Next, number 5. So this will be the last operation that we do, and that is the Cartesian product. Okay, so this is given by 2 sets, A and B. We write A cross B, like the times, so A times B. This is equal to the set of ordered pairs. Okay, so you know from analytical geometry, you have XY coordinates. So it's going to be the set of all the coordinates A, comma B, such that the first element there in the coordinates A comes from the first set. The order matters here. So the little a, that's the first element of the pair, comes from the first set. So little a comes from the first set, A. And the second element in that pair comes from the second set. First with the first, second with the second. Okay, so the order does matter here. Okay, so for sets, it doesn't matter. Cartesian product, it most definitely does matter. Okay, so we're going to look at a quick example. So let's say A is the set 1, 2, and B is the set A, B, C. Okay. So these can be anything. So A can be numbers, B can be something else. It doesn't matter. So what we want to do is form the Cartesian product. Okay, and we're going to do this systematically. We're going to pick the first element from A to be our first part of the point, and then we're going to look at all of the elements in B. So it's going to be 1 with A. So the 1 comes from set A, and the little a comes from set B. Then we're going to stick with 1, and we're going to have B. And we're going to still stick with 1, and we're going to have C. Now we're done with all of the elements in B. We go back to A, and we choose the second element. And we start from the beginning. So 2 goes with A, and then we go through all of them. So 2 goes with B, and finally 2 goes with C. And there's nothing more from B, there's nothing more from A, so we're done. Okay, so you just loop through both sets until you have all of the possible pairs. Okay, another way to look at this, if you want to look at all of the pairs between two things, we write A as 1, 2, and B as A, B, C. And we look at all of the pairs this way. So we're going to take 1 with A. Okay, so that row with that column. 1 with B. 1 with C. And we're done with that. 2 with A. 2 with B. And 2 with C. Now there's no more columns because we're done with B. There's no more rows because we're done with A. These are all of the pairs. Yeah, and that's what we listed out in the top here. Yeah, so it's just another way of making sure you have everything there. Okay. Any questions on the set operations? You're all good. Okay. Please, anything about sets before we move on to logic? You're all good. Okay, I told you, university, we move quick. Last chance. Anything? Yeah? Sorry, you need to shout you far away. Yeah? Oh, the power set. Power set with the empty set inside. Okay, so remember, the empty set is always a subset of B. We go back here when we did the subsets. Okay. Number 3, the whole set is always a subset. So B is always in the power set of B. The empty set is always a subset. So the empty set is always in the power set. You always have those two. Okay. So if we go back here to the power set, the empty set is always your first element, always. Then you go through the 1 element, 2 element, 3 elements, and so on. And then the whole set is always your last element. Okay, those two are always subsets. The first one and the last one. Okay, good. Okay, anything else before we move on? You're all okay with sets. Okay, next. Logic and set proofs. Okay, so we're going to go through a little bit of logic. We've done a little bit so far. It's been a bit, you may not have seen it explicitly, but we have done a bit. So we're going to go through logic and proofs. Now, the way that we're going to go through the proofs is using sets. So mainstream guys on Westville doing science and stuff, they do proofs with all other things. Our proofs that we're going to do for now are only going to be with sets. Okay, so if you're looking in the textbook and online and they start doing proofs with numbers and so on, no. Okay, our proofs are only with sets. Okay, so that cuts down your learning quite a bit. Okay, so the first thing we're going to look at and the first thing we're going to prove, just by the way, all of this is proving. Okay, every single thing we write down is going to be some proof. See, the level of fanning has gone up quite a bit. Yeah, shirt's also sticking to me. So we'll start off with logic and we'll save the set proofs for tomorrow. Okay. So a little bit to get through and then we'll be done. Okay, so the first thing is if we have sum A, we don't know what it is yet, so just sum A, and B or C. Okay, so we'll go be more precise in a bit. So we have A and B or C is equal to A and B or A and C. Okay, so the way we need to think about this is these A and B's and C's are called truth values. In other words, A, B, C can have the value true or false. Remember back to when we did the rules for the set? It can either be true or false. The same thing with this. So A, B, and C, they can't be numbers, they can't be fruits or whatever. They can only be true or false. We say that they are truth values. Or binary, right? True, binary. So true or false, 1 or 0, however you want to think about it. Okay. Now, what do we mean by A and B or C? Okay, so we're going to look at the bracket part with the or. So let's say we have B or C. What we want to do is determine the truth value of this combination, B or C, dependent on the truth value of B and C given. So if B is true and C is false, what is B or C? Okay, those are the type of questions we're going to look at. So we're going to write B and C like that. We're going to form a little table called a truth table. And we're going to look at B or C. Okay, So we want to know what is the value of B or C given B and C. And remember, these are truth values. They can only be true or false. So there's only so many combinations. So let's look at C. We're going to have true, true, false, false. And B is true, false, true, false. So writing it like this gives us all the possible combinations. So B can be true and C can be true. That's one possibility. Both of them are true. B can be false. C can be true. That's another possibility. B can be true, C can be false, or both can be false. Do you agree that's all of the possibilities? Okay. Because there's only two values. It can be true, it can be false. Now, what we're looking at is this combination, B or C. We've seen this before with those rules, right? We had X is even or X is a natural number, for example. And what did we say? The rule was satisfied if one of them was true, right? Either this or this. So true and true. What is true or true? True. Yeah, you get it. Pen's giving up. Okay, so true or true, that will be true. What about false or true? What do you guys think? False or true? True. One of them is true, so it's true. So true or true? True. False or true? True. True or false? True, yeah. False or false? False. Hey, you catch on very quick. Okay, so everyone understands that bit. Now, let's look at the second part here, A and B. We're going to look at that combination, and then we're going to put everything together to prove that statement. So we're going to look at, so let's just say here, that first bracket there, A and B, and then once we've done that, we can put everything together. And we're going to do the same thing. A has some truth value, it's either true or false, B as well. So there's only so many combinations. So we have A, B, A and B. So we're going to have true, true, false, false. Okay. So true, true, false, false. And then for A, we can put true, false, true, false. Yeah, that covers everything. Now again, from what we had before with the ands and the ors, let's figure this out. True and true. What's that going to be? True. Perfect. False and true? False. Who says true? Hands up if you say true. No, you can be honest, that's fine. Hands up if you say true. Couple. Hands up if you say false. And not everyone's putting their hands up. Either your hands up or it's not up. Okay, one or the other. Okay, we know that now. Okay, it's going to be false. Because if it's an and, it must be this and this. Both must be true. So false and true, false. Okay, everyone understand? No. Okay. If I want both things to be true, this and this, then what must the values of A and B be? True, yeah. Because I want this and this. Okay, say you go to the restaurant and you order fish and a Coke. Right, the waiter comes and he just gives you a Coke. Is that what you ordered? No. Why? Because you ordered this and this. If the waiter comes with just the one thing, he did not give you your order. Now the waiter comes and gives you your fish and your Coke. Is that what you ordered? Yeah, there you go. Okay, must be both. Okay, true and false. False, yeah. So true, the waiter did give you your fish. False, did not give you your Coke. Well, that's not what you ordered. False. False and false. The waiter did not give you your Coke, did not give you your fish. Did you get your order? No, it must be false then. Make sense? The only way for this to be true is if both of them are true. You must get both parts of your order and then you got it. Make sense? Cool. Okay, so we have the so-called truth table. Okay, this table here for B or C. And we've got this truth table here for A and B. So everyone's okay with writing them out. Okay, so these are the two simple ones, so or and. Now we're going to look at the more complicated case of the combinations. Okay, and then we're going to prove the statement here, statement 1, and then statement 2, that will be for homework. Okay, once you do the first one, second one's quite easy. Okay, so what are we going to do is set up a very big truth table. So for the first part, this left-hand side, we need A, B, and we need C. Right? We need all of this. So we need A, we need B, we need C. Right? Those are all the variables we're working with. Now we need B or C, we need that combination. So we're going to put that in our table. That's going to be in our table there. And then finally, we need A and B or C. That's going to be the last part of our table. Okay, does everyone see how we built up the table? So we have A, B, and C. Those are all of the variables. Then this column here, so let's just write it all out. Okay, so this column here, B or C, that's that second part of the statement. Okay, we're just breaking it up into smaller parts. So we have B or C, that's going to be one column in the table, and A and B or C, that will be the final column. Okay, does everyone see how we did that? Okay, so we're just breaking it up into smaller parts. Okay, so here it's going to be a little bit more complicated because we've got three things. So it's going to be true, 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 false, false, false. Sorry, there's a nicer way to do this. Okay, sorry. So for the first column A, I'm going to put 4 T's and then 4 F's. Makes it a bit easier just to keep track of everything. So we're going to have true, 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 false, 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 false. Yeah, it just makes it a bit easier just to make sure we have everything there. The second column, I'm going to put 2 T's, 2 F's, 2 T's, 2 F's. True, true, false, false. True, true, false, false. Okay, so it's just pairs. And then the last one is going to be true, false, true, false, true, false. And that covers everything. True, false, true, false, true, false. Yeah, you should end up with FFF. That means you have everything there. Okay, so let's go through it. B or C. We did it before, but we're going to do it again as a refresher. So we're going to look at B, we're going to look at C, and we're going to look at the truth value of the combination. So for the first one, true or true? True. True or false? True. False or true? True. False or false? False. True or true? True or false? No, not false. True. One of them is true, so it's true. False or true? True. False or false? Okay. Mostly correct, so I'm happy with that. Okay. Next, we're going to look at the combination of what we've done. So that's the full expression A and B or C. Now that B or C we've already done, so we don't need to worry about that. So we're looking at A, that first one, and the last one that we did. We're going to AND them. Yeah, I think you guys got it there. Okay, so true for the first one, and true for the second one. True. Next one. True, Next one. Very good. Next one. False. Very good. Next one. Very good. Next one. Nice. Next one. Yeah. Next one. Perfect. All of them correct. Well done. Okay, so this gives us the full truth table for the left-hand side. Everyone see that? So that left-hand side there, the A and B or C, we got every single possibility for A, B, and C, and this is the output. So if A, B, and C are true, 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 we get true. If it's true, true, false, we get true. Okay, we look at every possibility, and that is all of the outputs for the left-hand side. Now, take a guess. What are we going to do now? The right-hand side. Exactly. So we're going to do exactly the same thing for the right-hand side. And what happens if we find that these two truth tables are the same? It means the statements are equal. Because if the left side is equal to the right side for all of the possibilities, well, then they're equal. That's what we're trying to show. We're going to show that this left-hand side is equal to that right-hand side. Okay, so we're going to build up our truth table. We need A, B, and C again. And we also need A and B. That's going to be one column. You know, we're breaking it up. That's going to be one column. What is another column going to be? A and C. That will be another column. And what's the last column going to be? Yeah, the whole thing we put together. Exactly. Okay, so we have A, B, C. So the first thing we need is going to be A and B, and then A and C, and then the combination. So it looks like a lot, but it's quite easy to fill in once you've set it up. Okay, so we have A and B, A and C, and then finally the whole thing. And then it was all A and C. Okay, so that's all of the columns. Okay, of course you're going to write it out neater than this. Okay, then let's put in our columns. Yeah. Okay. In the test and exam, please use a ruler. Okay, I'm freehanding here, but try and make it a little bit neater for the presentation. And then the last thing, we just leave it like that. Okay, now we need to fill it in. Same thing as before. We look at the first column. We put 4 T's, 4 F's, and that's how we know we have everything. So it will be true, 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 false, false. Yeah, sorry. Missing one there. True, true, true. That's 4 of them. False, 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 and one more that makes 4. Okay, so we got all of those. Then the next column will be true, true, false, false, true, true, false, false, and so on. So it'll be true, true, false, false, true, true, false, false. Okay, so that's all of the 2's. And then true, false, so on. Okay, and we ended off with false, 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 so we know that's everything there. And we just fill it in exactly the same as we did before. So I'm just going to let you shout out quickly. So let's just fill it in column by column. So this first column, A and B. So we're looking at the first one for A, the second one for B, and we're putting the and. Okay, so let's go. First one. Next one. Next one. Very good. Next one. Very good. Next one. Next one. Next one. And last one. Very good. See, it's very quick. Once you've set it up, you just put in the values. Okay, now A and C, we're looking at the first one and the third one. So just quickly look through. Give me the answer. First one. Next one. Next one. Nice. Next one. Very good. Next one's false. Next one. Next one. Next one. Very good. So we have everyone there. Finally, we're going to look at the last two columns we did, and we have to put an or between them. So again, last two columns, let's put the or. So the first one, good. Nice. Next one. Yep. 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 And last one, false. Very good. Yeah. Again, very quick. Once you've set it up, very quick to put through. Now, what we have here is the truth table for the left-hand side. We've got the truth table over here for the right-hand side. If the truth tables match up, it means the left-hand side is equal to the right-hand side. Yeah, and you can quickly check. You just check down that last column there, and we check down the last column here. They're the same. Okay, last columns are equal. That is, means we proved it. So left-hand side equals right-hand side. Okay, any questions about truth tables? All good. So this is proof number 1. Okay, so this one. Number 2, that will be for homework. Okay, so number 2 will be A or B and C. We want to show that this is equal to A or B and A or C. Okay, so very similar to that previous one. So for homework, left-hand side, you set it up, A, B, C. You find B and C as one column, then you do the combination. That will give you the left-hand side. For the right-hand side, you'll have A, B, and C. You find A or B, that will be one column. A or C, that will be another column. Your final column will be the combination, and then you check that they match. If they match, it means both sides are equal, so the statement is true. Yeah. Does everyone understand how to do the homework? Okay, so that one is for homework. And then these last two will also be for homework, but we will start with them next time. So number 3. So I'm not going to give you any hints. I'll see if you can figure this out on your own. And then tomorrow we'll go through it. So not A or B is equal to not A and not B. Okay, I'm not going to give you any hints. I'm sure you can figure it out. Anyone figured it out already? What does this mean? If I say not A, sorry?
It's not making it screen on.
Not quite. Remember, A and B can only be true or false. So if A is true, not A is. And if A is false, not A is. Yeah. So you should be able to figure that out. So that one, and then number 4, not A and B is equal to not A or not B. Okay, numbers 3 and numbers 4 there, those are very, very important. Those are called the De Morgan's laws for logic. Okay. Okay, so please put a box around number 3 and 4. Okay, we're going to use that quite a lot in the set proofs. Okay, so numbers 1 and 2, they don't really have names, but 3 and 4, those are called the De Morgan's laws. So when I say De Morgan's laws, you should know what I mean there. Okay, so you can try number 3 and 4 out for homework, but that's what we're going to start off with tomorrow. And then we're going to look at set proofs, just as an example. So don't take this down. This is just something we're going to be looking at. This will be, yeah, if this pen would work. There we go. So don't take this down. This is just an example for tomorrow. The set difference of B and A, so B minus A, union C minus A is equal to the union of B and C, set difference with A. So this is like a set identity. Given any three sets A, B, and C, this is always true. And we want to prove this. Okay, so the question we're going to be doing tomorrow will be similar to this. I've got 12 here. We'll see how many we get through. And then this will also be in your quiz, okay, for next week. Okay. And that will be the last thing for the quiz, will be these set proofs. Okay. Any questions for this truth table stuff? Everyone good? Okay, so please do these homework problems, especially number 2, especially. If you want to try out 3 and 4, please go ahead. That we'll start off with tomorrow. Does everyone know where S3 is now? Did you all go find it? No. Okay, there's people nodding, there's people shaking their head. Who knows where it is? Put your hand up. Okay, a few of them. Okay, you guys show the others where it is, if you're feeling generous. Otherwise, find it yourself for tomorrow. Okay, remember, it's tomorrow at... Go to the timetable. Yeah, there we go, 8:40. So you have a bit of time. Please make sure you know where it is. Okay, so here, MATH160, S3. Okay, please make sure you know where it is. Also, for next week, Tuesday, you need to know where the DC building is. I know for engineering, you have tutorials there as well. Please make sure you know where that room is. Okay, so Desmond Clarence, follow the signs up to Desmond Clarence there. It's the 4th floor. You'll see the sign nursing. Okay, and there'll be a big room full of computers. That's when you know you're at the right spot. Okay, so S3 for tomorrow, and for next week, make sure you know where DC is. Okay, any questions before we go? Yep.
You show us yes, with that observed
Oh, the tutorial groups. So you go down here, a little bit down to the tutorial groups. There we go. You click on this, and that will be all of the student numbers and your groups there. Okay. So on the day, the tutors will be labeled A, B, C, D, right? They know their numbers, their letters, so they'll, you know where to go. Okay. So at the beginning, I'll say tutor A, you'll put his hand up, you'll follow him. And tutor B, you follow them, and so on. Okay. But just make sure you're in DC so that you know where to go with the tutors. If you come late, tutor's not going to say, oh, I'm tutor B, you're just going to be lost. Okay. So make sure you're on time so you can find your tutor. Okay. Yeah?
when you have access to this.
Learn page. Learn 2026. Have you been there? No. Okay. Make sure you have access. If you don't have access, please send me an email. It is very important that you have access to this because the quizzes and the tutorial test will be online with this. If you can't access it, what are you getting for the quiz? 0. Okay. Make sure you have access by Tuesday, next week Tuesday. You can't come to me on Tuesday saying, I don't have access, I can't do the quiz. I'll say you're getting 0 for the quiz. Okay. Next week Tuesday, please make sure. Anything else? All good. Okay, we'll leave it at that for